As you are all aware, charged particles move easily along magnetic field lines. And in the magnetosphere, what this means is that if you have a measurement at one point, you're often interested in where that field line ends up if you would follow it to some other location. In particular, if you're interested in magnetospheric-ionospheric coupling, and if you have a measurement in the ionosphere, you'd often like to follow the field line through that point into the outer magnetosphere to see where it leads to. This is a subject I would like to talk about today, and I'll do it by discussing a recent quantitative magnetic field model that Gil Mead and myself have developed. Now, of course, when you're near the Earth, an internal model is usually a good enough approximation. As you get further out into the magnetosphere, you have to take into account the external currents, and this is what we've been concerned with our model. I'd like to begin by saying just a little bit about the model. What we have done is to represent the disturbance field of these currents in the magnetosphere with a power series expansion, keeping terms through quadratic. Now here I've tried to represent some of this three-dimensional information on a two-dimensional slide, and I'd like to take a minute to explain it here. First, look at the bottom portion of the slide. I've taken constant latitude circles here, projected them out to the equatorial plane along field lines. Of course, a dipole would project out to the equatorial plane as a circle, and when you're in close there, it is almost a circle. And as one goes out further, one sees more and more distortion. The dashed lines here are the constant meridian planes. Of course, a dipole would be radial, and so the curve here is due to the sweeping back of the field lines. Because our model is not really good out into the tail, on the top of the slide, I've projected the field lines onto a plane cutting through the tail at 10 Earth radii behind the Earth. So think of this as just a plane cutting through the tail, 10 Earth radii behind it. And again, one can see where the constant latitude, constant local time surfaces intersect this plane through the tail. Now, I won't say much more about this particular slide, but you see it's useful for taking any low latitude measurement and seeing where the corresponding field line goes to in the equatorial plane. So now I'd like to take some older experimental data you're probably familiar with, low altitude data, and use this type of figure to project it to the equatorial plane and the tail. Some years ago, McDermott and Burroughs looked at trapped particle data on a low altitude satellite and determined a high latitude cutoff for trapped particles. And they suggested that this was due to that the particles were trapped out to the last closed field line. And so here it's of interest to see whether the last closed field line of our model corresponds to what they would determine as the last closed field line. I've taken their outer line, their longitudes, and used my model to project those particular points to the equatorial plane. They are shown as the dashed lines here, and the heavy line here is the last closed field line of the model. So to the extent these dotted lines go out to the solid line, there is good agreement between their data and the model. Let's say this is a convection pattern you've seen a lot of today. I projected the sunward convection region. That's what's shown by the shading here. Both the Hepner's data and the Kaufman-Gurnett picture, which is quite similar. Since I'm running short of time, let me just point out that most of the region outside the plasmapause and inside the magnetopause, of course, is the sunward convection region. We can't really say if the sunward convection, or if the convection is sunward all the way out to the magnetopause or not. I think that's an important question, but it can't be answered by this method. In summary, just let me point out that these models are all static models. However, we know that certainly the real field is not static. So the models are primarily of use in projecting average data. One must always keep in mind that the field is actually very dynamic. I just want to emphasize this point, and because I feel it is very important, and certainly the models cannot take into account the rapid changes that do occur during substorms.
All right, about time. A fields person got up on the screen there. These petty squabblings about which ion do you like, or ions versus electrons. I was waiting for the electric field teams to be here. Anyway, I don't know about the rest of you, but I've loved these videos, and I've loved the personal stories that were shared. I do feel a little bit like the person that was told it was an informal dinner and you show up and everybody's in a tux. I'm very, Don Fairfield certainly was one of my role models earlier in my career. Actually, the fact of the matter is he still is. And I'm very proud to have overlapped with him for about 20 years at Goddard. Having said that, I was 5 years old when he started at graduate school. So if you're interested on whether or not he was dating, Joe Borowski's girlfriend at the time of his defense, I'm probably not the person that could fill you in. Don will enjoy that. That's the kind of rumor Don would enjoy. I'm not sure about Joe Grabowski, but they would enjoy that. He would enjoy that rumor if you want to start it. But you're one of the other Penn Staters. Oh, be careful. Wasn't Dick Goldberg there too? Okay, I was 5 at the time. I was a little bit older later on, and I tried to pay attention when I heard the stories. So, thank you. And actually, I would enjoy audience participation. Actually, quite seriously, these presentations, I've loved them, and what I keep thinking to myself over and over again is, my goodness, when you get the right person with the right interests and drive and skills is at the right place and the right time, to actually undertake those tasks, just wondrous things happen. And I think it's true of almost all the people that have been honored here at this meeting, and it is most certainly true of Don Fairfield. So, again, feel free, particularly people that are a little more senior than I am, to chime in. But Don Fairfield arrived at Penn State, I believe, in 1960. And there was quite a group of people that arrived in this meteorology department. I think most of them were probably already destined, perhaps thanks to the space age, to go into ionospheric physics. But what was it? Okay. Okay, I knew the meteorologists were still in there somewhere. Was Peter Banks there too? Okay, I knew it was about a half a dozen people. I didn't know it was this many. The remarkable thing that happened, though, is there was a young English professor, and I now know that 3/4 of the room probably know the story better than I do, by the name of Jim Dungy, who came over. I believe he actually arrived for his first visit before his famous before Dungy 1961 had actually appeared. And this was, of course, a pivotal point for the development of magnetospheric physics as a field. And there was Don Fairfield, literally, in the midst of this very distinguished group of graduate students, was standing there, I think as he put it to me once, as a vessel waiting to be filled. And I'm sure that wasn't the case for some of you, but Don certainly felt that it was. Don was publishing papers by his 3rd year in graduate school. They were all oriented towards fields, magnetic fields, the currents that are necessary, they're necessary to support them. Fairly soon thereafter, he wound up at Goddard, and it continued to be the same type of situation. Without going into details that only probably 2 or 3 of us would enjoy or find interesting. The Norman Ness magnetometer group had just recently come into its own. There was an earlier group that focused primarily on the ionosphere. That was, of course, the Hepner team. But the Ness group was off and running, and Don Fairfield found himself in the environment that he loved most, namely being buried in fairly high-quality measurements. IMP2, IMP4, IMP6 in particular, Norman Ness more or less turned those over to him. By the way, I don't know, nobody was ever able to explain to me why the odd-numbered missions all perished, if you will, at Goddard. I think three, I don't believe three did well. I've never heard of 5. 7 got into orbit, but I think it had so much interference it never worked. And IMP8, Ron Lepping owned IMP8 for other areas. It was a period of time where there was either your instrument or it wasn't. And if it was your instrument, a man, or in rare occasions back then a woman, but a scientist, if it was their instrument, they analyzed their data. And that, of course, is the great strength that Don Fairfield brought to his entire career. He was a pathfinder in the analysis of magnetic field data. As you heard in this piece, the Meade and Fairfield model, which grew out of this, what you heard here, basically was the first global magnetospheric model that was available, so people could actually look at their charged particle measurements or look at their electric field measurements and try to map them to other locations. But you notice, if you're interested and you listen very closely, already there's Don Fairfield more or less on the mountain. He's already warning you about how quickly it reconfigures. Many people went on and raised the state of the art to a very high level in producing these average magnetic field models of the magnetosphere. But none of them can get around the fact that the point at which those field lines cross the equatorial plane in the tail, it changes by 1 to 10 Earth radii per minute, at least during any interesting period of time, and you're probably not doing this work unless it's a dynamic period. And here's Don Fairfield this early in the business, the first model he's involved in, and already he's cautioning people. Incidentally, this does speak directly to what I said earlier about Don being a pathfinder. He got into an area, he did the best possible work that he could do, and then he moved on to something else. And he was very supportive of people that came after him. He encouraged them, and if there was anything he could do to help them do a better job than he did, he would certainly go that extra mile. But the fact of the matter is, he undertook a problem, he did his best, he had his say, and he moved on. And the record of contributions is really incredible. I think probably most of us in this room have certainly used his boundary models, whether it's the bow shock, the magnetopause, or the cross-tail current layer. There's probably 30 cross-tail current layer models, and if you're doing anything with plasma or charged particle distributions in the tail, this is one of the most difficult to model and one of the most difficult to use boundary models there is. There were many before Don Fairfield. There were many models afterwards. If you open JGR, just about any given month, you'll find the Fairfield model is the one that's used most frequently. Don went on through his career to eventually, more or less, I would say, achieve some sort of peak with the geotail work. His work on Kelvin-Helmholtz in geotail was particularly striking. Now, do the arithmetic with me. Don published his first paper in graduate school in 1963. And I've had to do this several times because no matter what I do, Don Fairfield is emeritus at Goddard. He's still doing research. And I keep getting a number of like 51 years. Yeah, I keep trying to make it 40, but it's not. It's 51 years. I'll end with just a couple of personal observations about Don. Again, when I was at Goddard, Don tended to work by himself. I, of course, had my collaborators. A few times we did something together. But I remember in talking with Don, and he always viewed magnetospheric physics as a magnificent puzzle to be solved. And actually, he often used that metaphor. He had a file, and yes, in this room I don't have to say I'm that old, But it was actually a folder with a little rubber band or a tie strap, and it was labeled funnies. And Don never took any measurements that were made and looked at them and said, something's wrong. The gods are playing a joke on us, or the spacecraft was having trouble and we'll never figure out what it was. He never took a piece of data and said, I just don't believe that and I'm not going to spend my time on it. He put it in this folder, and he labeled it the funnies. Now, to be honest, I never quite got that. Apparently, he did compare it to cartoons, but on rare occasions, either informally at meetings at Goddard, or a few times at conferences, he pulled out his funnies file. So these would be magnetopause crossings where the pressure on the outside is 5 times what it is on the inside. And the question is, can you really prove that it was, for some reason got hit with a huge interplanetary, it'd have to be really huge, interplanetary shock, and it was collapsing back towards a new equilibrium, farther in. I mean, this was a puzzle piece. And he hung on to them, and he worked them, and sometimes 15 years later, their paper would come out, and he would have figured a way to tease this out of the data. Later, when people like Baker had been a bad influence on me, and I wound up with administrative or management responsibilities, I always felt bad about Don Fairfield because I said, look at his capabilities. He's doing all of his own software. Oh wait, what was it? Fortran? Was it 4 or 3? 2. Actually, at one point, he had a computer he was very comfortable with and a compiler that he liked to use for his data analysis. It was so old, there wasn't an IT person in the building that could have fixed anything if it died. But I said to Don, I said, look, we're not rich. We have to write proposals, at least by that time, like everyone else. And I said, I'm going to give you half my programmer for my data analysis, half time. And he said, Jim, that's not how I work. And I said, well, how about, we'll get some grad students and some postdocs. And he said, no. He said, why are you trying to cripple my program? And I said, what do you mean? And he said, I look at the data myself, and I figure it out, and that's how I make my contributions. And he said, you do it the way that works for you. And he said, please let me do it the way it works for me. And I thought that was just an incredible wisdom to know and understand himself in that manner. And again, it was a privilege to have gotten to interact with him and observe him during that period of time. I think that's my 5 minutes. Does anybody want to shout out something, any particularly poignant Don Fairfield interaction, anything involving dances or fist fights? If you ever told Joe Grabowski he didn't believe the plumes went that way, anything like this would be fine.
He was very well behaved, very softly spoken.
Oh, yes.
And very exact in touches he indicated, doing what I consider by my standards the right thing, which is trust nothing.
Yes, and I would also add to it, and for some of us this is a little disappointing, he never shared a single juicy story with me. And from as nearly as I can tell, he never shared one with anybody else. And I know he was there for some very interesting periods, through some very interesting times at Goddard. I think I better stop.